Of alpha decay, we will discuss about the background of alpha decay. So alpha decay occurs in radioactivity. We know that all substances are made up of atoms. Atoms have electrons that are orbiting around the nucleus, and a nucleus is located in the center of the atom. There are protons and neutrons in the nucleus, and the size of nucleus is very small. In some type of atom, the nucleus is stable, unstable, and will decay into a more stable atom. Basically, when the number of proton and neutrons are equal in the nucleus, this atom is considered as the stable nuclei. When number of protons are greater than neutron, or number of neutrons are greater than number of protons, the atom is no more stable. This atom is considered as unstable nuclei. This type of unstable nuclei undergoes the spontaneous emission of radiations to go into stable state. This spontaneous emission is known as radioactive decay. It is known as spontaneous decay because energy in this process is released from the nucleus in the form of radiations. When there is spontaneous emission, energy is released. We will get energy from the atom. So this is known as spontaneous emission of the radiations. As we discussed in previous slide, radioactive decay occurs when an unstable nuclei decays or there is spontaneous emission of the radiations. There are three modes or three ways in which radioactivity decay can be happen. It may be alpha particle. We use the symbol alpha. There may be a beta particle emitted as a result of the spontaneous emission, whose symbol is beta, and there will be chances that a gamma rays will be emitted as a result when the unstable nuclei undergo the spontaneous emission. Radioactivity is basically a natural phenomena of our environment. It was first observed by the French scientist Henri Becquerel when he used uranium to exposed on the photographic plates. He noticed that some type of radiations were emitted by uranium salts. There exist almost all the stable chemical elements from the lowest hydrogen to highest bismuth on the earth. When we go above the atomic number 83, all elements are mostly naturally radioactive. Mostly alpha radioactivity has been observed in all nuclei above atomic number greater than 82. Because as we go to the high atomic numbers, as we discussed earlier, number of proton and number of neutron in the nucleus are no more equal. So they are unstable nuclei. To go into the stable nuclei, all higher elements undergo the radioactive process. This is the natural process. Now we will discuss about what are the alpha particles. Alpha particles are mainly made of two protons and neutron. Their proton number is 2. This means that they have charge of +2 and their atomic mass is 4. As we know that atomic mass comprises of number of protons and number of neutrons, so there is 2 protons and 2 neutrons, and their mass will be 4. The mass of alpha particle is casually measured in atomic mass unit, where each proton and neutron equals 1. We can write them as alpha 42. They are also known as helium nuclei because their mass, atomic mass, is exactly equal to atomic mass of helium, and they have proton number that are equal to the number of protons present in helium. So we mostly call them as helium nuclei. Alpha, as their charge is, they carry the charge of two protons, so they are mostly slow in speed and heavy as compared to beta and gamma particles. They have low penetrating power due to heavy charge. We can stop them just a sheet of paper. Their penetrating power is very small in comparison with beta decay or gamma decay. Because they have large charge, alpha particle ionize, they can easily pull electrons from other atoms strongly. If we compare their ionizing power with beta particle or gamma particle, alpha particles ionizing power is greater. This is all about the alpha particles. In this slide, we have thoroughly discussed about their charge, their mass, what is the penetrating power of the alpha particle, and what is the ionizing power of the particle. In the previous slide, we have discussed about the alpha particle. Means we discussed what is alpha particle, its ionizing power, its penetration power, etc. Now we will see how this decays occur. Let us take up radioactive nuclei, that is uranium. Its mass number is 238 and proton number is 92. In uranium, you can see that there are 146 neutrons and 92 protons. Number of neutrons and protons are not equal, so we will consider it as an unstable nuclei. Uranium 238 92 is a natural firstly discovered radioactive nuclei that was discovered by Henry Becquerel. When it goes into the stable state, it undergoes the spontaneous emission of the alpha particle. So this is known as alpha decay. Here you can see that radioactive nucleus goes into the new nucleus, that is thallium 234-90. In thallium there are 144 neutrons and 90 protons. Along with the emission of the alpha particle that contains 2 neutrons and 2 protons. This is the basic diagram or systematic example of the alpha decay. In the periodic table, if we move towards the high atomic number nuclei, mostly all nuclei with atomic number greater than or equal to 83 decay by alpha decay. Mostly there will be alpha decay when we go towards high atomic numbers. Alpha decay is also known in the tin region. This is the basic introduction to the alpha decay, how it occurs, how a parent nuclei or radioactive nuclei changes into the stable state or by doing the alpha decay. Now we will see here is a general expression for alpha decay. Generally, a daughter nucleus, parent nucleus is represented by X. A shows the atomic number of the parent nuclei. Z shows the proton number of the parent nuclei. When it goes into the stable state by undergoing the alpha decay, as we know that the atomic number of the alpha particle or helium nuclei is 2 and the mass number is 4. So when there is a daughter nucleus whose mass number is decreases by 4 as compared to parent nuclei, and the atomic number is decreases by 2 as compared to the parent nuclei due to the emission of alpha particle. Here are the some examples of alpha decay. NP shows the neptunium whose atomic number is 93 and mass number is 237. It goes into the daughter nucleus, that is protactinium, whose atomic number is 233 and mass number is 233 and atomic number is 91, along with the emission of helium nucleus. As you can see that the atomic mass of the protactinium is decreases by 4 and the atomic number decreases by 2 due to alpha decay. Similarly, in second example, platinum and radioactive elements whose atomic mass is 175 and atomic number is 78 undergoes the radioactive decay by the emission of alpha particle and the daughter nuclei is osmium. The atomic number of the osmium decreases by 4 and it is 171. Similarly, proton number decreases by 2 and it becomes 76 due to the emission of helium nuclei. Third example is gadolinium, in which gadolinium, a radioactive element whose atomic mass is 149 and atomic number is 64, undergoes the alpha decay by the emission of samarium element whose atomic mass is 145 and atomic number is 62. In all three examples, you can see that the mass of daughter nuclei decreases by 4 and the proton number of all daughter nucleus decreases by 2 as compared to parent nuclei. This happens due to the emission of the helium nuclei. As we know that radioactive process is a process in which there is a spontaneous emission of the radiations. So we can say that amount of energy is released in this process. So similarly in alpha decay, the emitted particles are alpha particles are monoenergetic. Their energy range lies from 1.8 to 11.6 mega electron volt. Mostly the range will be 4 to 9 electron volt. As we discussed earlier, the ionization power of alpha particles are high as compared to beta and gamma rays. So when their ionization power is high, due to high charge, they cause strong internal radiation hazard, but their penetration power is small in comparison with beta and gamma rays. Their penetration power is so small that you can say we can stop alpha particle by a piece of paper. So they can cause internal radiation hazards than an external hazard. The natural occurring alpha emitter form long series of nuclei that decay to one another. Some of these naturally occurring decay series involve isotopes of radon, that is an inert gas. This is the basic introduction of the energy and their hazards of alpha decay. Now we will discuss why alpha decays occur. This graph is basically shows the stability of the nuclei and how their behavior changes. The stability of any nuclei can be derived by taking the ratio of number of neutrons to the number of the protons. For the lighter nuclei, in nucleus, number of protons are mostly equal to number of neutrons, so the ratio is 1. And this stability ratio works properly when the number of protons and neutrons are equal. So we can say that in this graph, black line shows the atom or nuclei whose stability ratio is 1. As we move towards the higher atoms or nucleus in the periodic table, the number of protons and number of neutrons are not equal in the nucleus. So if we take their ratio or to find the stability of the nucleus, it will be not 1. In some nucleus, the number of protons are greater than number of neutrons. Similarly, in some nucleus, the number of neutrons may be greater than number of protons. If we have a look at the graph that is drawn on this slide, black dots shows the atoms with stability ratio 1. In that atoms, number of protons and number of neutrons are equal. But different colors shows different decays that include beta decay, beta plus, beta minus decay, alpha decay, gamma decay. Below the black line, there is purple line that shows the beta negative decay. Beta negative decay occurs when there are large number of protons as compared to there are large number of neutrons as compared to protons, and in beta minus decay, neutron changes to proton. It means that there will be beta minus decay. But above the black line, there is sky blue curve line. This shows the beta plus decay. This means there are number of protons in the nucleus are greater than number of neutrons, and beta plus decay occurs. In beta plus decays, proton changes into the neutron. Yellow area shows the alpha decay. We discussed in our previous slides. Alpha decay occurs for atomic number Z is equal to 83 or greater than 83. So you can see in this graph Z is equal to 82. For Z is equal to 82, the most of area is yellow. This shows the alpha decay. In this slide, we will discuss why alpha decays occur. What is the reason that alpha decays occur? Why this decay happens? Alpha emission is a Coulomb repulsion effect. Basically, alpha decays attempt to create a more stable nuclei by expelling a particle made from two of the atoms of protons and two of atoms radiations. As we know that the atoms are stable for low atomic numbers, but as the atomic numbers increases, the instability increases gradually, and the nucleus has to lose protons to go into the stable area. Alpha decay mostly occurs in heavier elements, as we discussed in our previous slides that alpha decay occurs mostly for Z is equal to 83 or greater than 83. Because the massive size of the nucleus makes it difficult to balance the repulsive effect of the electromagnetic forces that may be Coulomb repulsion forces when the proton repel each other with this strong nuclear force trying to hold the nucleus together. When the number of the protons increases in the nucleus, the Coulomb repulsive forces also increases. So there is no balance in the nucleus. To balance these forces, removing proton from the nucleus helps to increase the stability of the nucleus. But the alpha particles allows the nucleus to reduce its size by 4 nuclear particles while decreasing the effect of the proton significant. So this is the reason that when their number of the proton increases in the nucleus, the repulsive forces are also increases. Alpha particle helps to balance the nucleus by removing 2 electrons and 2 neutrons from the nucleus, and the parent nuclei or radioactive nuclei tends to form the stable state as compared to the unstable condition. This is the reason behind why alpha decay occurs in radioactive decay. Mostly the alpha decay is considered most probable in heavy nuclei. It means that the unstable nuclei tend to undergo the alpha decay to go into the stable state. It is the most convenient or probable way in the radioactive decay. Alpha particle is very tightly bound system whose binding energy is 28 mega electron volt. In heavy nuclear, energy required to pull out the last nucleon is about 8 mega electron volt. That is the energy required for alpha emission. We can calculate it as 4 into 8. There 4 shows the 2 proton and 2 neutron for helium or alpha particle. That becomes 32 minus 28. That is the binding energy for alpha particle. When we calculate, it becomes 32 minus 28, that equals to 4 mega electron volt only. That is very small amount of the energy, very low value of the energy. We can say that for alpha cluster it becomes more easy or convenient to come from the nucleus than single nucleon or other complex nucleus. It means that to remove the alpha particle from a nucleus, from a nuclei, is easy as to remove single nucleon. Thus we can say that alpha decay is more probable decay mode in heavy nuclei than other decay modes like beta decay or gamma decay. This is the reason that alpha requires small amount of energy to remove to come out from the unstable nuclei. So this is the most probable way of the decay in heavy nuclei when the stability ratio doesn't work properly. As compared to beta or gamma decay, this is the most convenient, easy way. This diagram shows the spontaneous emission of the alpha particle. What is the mean of this spontaneous emission? Spontaneous emission says that when our parent nuclei is at rest and it goes into the stable state by emitting the alpha particle along with another nuclei, it comes out as the kinetic energy of the alpha or daughter nuclei. Alpha particle is more stable and more energetic particle. This is the spontaneous emission of alpha particle. The rest mass of the parent nuclei appears as the kinetic energy of the second reaction that happens as the release of the alpha and the daughter nuclei. This is the spontaneous emission of alpha particle. We can see that here is an X nuclei whose atomic number is represented by Z and atomic mass is A. It undergoes the spontaneous emission of alpha particle along with another nuclei that is represented by X bar. Spontaneous emission means the big amount of energy is released in this process. So this is known as the spontaneous emission of alpha particle. Alpha particle carries the large amount of energy along with it, and it is considered to be more stable nuclei as its stability ratio is equal. Neutron to proton ratio is 1. Now we will discuss the conservation of energy and the conservation of the momentum in the alpha decay. First equation shows the spontaneous emission of alpha decay that can be represented as XAZ that decays into XZ bar, that is the data nuclei, plus alpha. The alpha particle, as shown by Rutherford, is the nucleus of helium consisting of 2 protons and 2 neutrons in the nucleus. To understand the decay process, we have to study conservation laws of mass, momentum and angular momentum. First of all, we will discuss about how energy is conserved, or what is the conservation of energy in the alpha decay. This will be thoroughly discussed in these equations. First, we will consider that for conservation of energy, we will assume that initial atom, that is our parent nuclei, represented by X, having atomic mass A and atomic number Z, is at rest. The initial system thus have rest mass energy of nucleus X mxc square. The kinetic energy for initial system or for parent nuclei is 0. Then when daughter nucleus formed by the spontaneous emission of the radiations and radioactive decay occur, now the final system will contain X bar, that is the daughter nucleus, and alpha nuclei. Both are in motion. The daughter nuclei and alpha nuclei, as we discussed earlier, are in motion. So due to motion, they must possess kinetic energy along with the rest mass energy. So when we will put the values of energies and kinetic energies for initial reaction, kinetic energy, as we discussed, is 0. So as we know that rest mass energy can be written as E is equal to mc square. Putting the value of E for X, that is parent nuclei, we have mxc square is equal to, on the right hand side for daughter nuclei and alpha nuclei, as we discussed, there must be a kinetic energy because these two nuclei are in motion. So mx bar c square represent the rest mass energy plus tx bar. Here tx bar shows the kinetic energy of the daughter nuclei. For alpha particle, we will write plus m alpha c square. That represent the rest mass energy of the alpha particle plus t alpha. That is the kinetic energy of the alpha particle. We will arrange our masses on left hand side. Mx is minus mx bar minus m alpha, taking the c square as common on one side of the equation. It becomes equal to tx bar plus t alpha. If we note that the quantity of on left hand side of equation is the net energy that released in the spontaneous emission of alpha radiations, that is known as Q value. So we can write Q value as Q, that is equal to mx minus mx bar minus m alpha c square. Comparing this equation with equation 1 with the above equation, we can write Q in the form of kinetic energies as Q is equal to Tx bar plus T alpha. The condition for this decay is that the decay will occur spontaneously only if Q is greater than 1. For the value of the Q, that is the energy that released during the emission, there will be no emission. If Q is less than 0, the emission will occur only if Q must be greater than 0. This is the conservation of energy. In previous slide, we have discussed about the conservation of the energy. We have calculated Q value. We know that if Q value, the amount of the released energy as a result of the spontaneous emission of the radiation. If the Q value is greater than 0, then the spontaneous emission will occur. This has been discussed in previous slide. This is the condition for the Spontaneous emission of alpha decay or radiations have to occur. If Q value or in value of the energy released during the spontaneous emission is less than 0, then the decay will not occur. So here is a sample problem. In this sample problem, we will calculate the Q value. The sample problem states that is plutonium unstable to alpha decay. This stability will be calculated by calculating the Q value of the reaction. We will calculate the Q value of our reaction. On the basis of the result, we will conclude that is it possible for plutonium to alpha decay or not. This is the equation for plutonium decay. Plutonium consists of 94 protons. Its atomic mass is 236. When it undergoes the radioactive decay or spontaneous emission, daughter nuclei uranium, whose atomic number is 92 and mass number is 232, is formed along with alpha particles and the release of energy. Here energy released is represented by the Q. As we discussed in our previous slides, the Q is value or Q energy released is equal to the rest mass of the parent nuclei, that is the plutonium here, minus rest mass of the daughter nucleus that is formed, that is in this reaction is uranium isotope, minus rest mass of the alpha particle into C square. We can say that Q value will be calculated if we take the difference of the rest masses of the left hand side minus rest masses of right hand side on the equation. If we take the differences in both the masses, we will get Q value. Putting the values of the rest masses of all the elements, Q is equal to 236.404607 U, that is the rest mass of the plutonium, minus 232.037168 U, that is the rest mass of the uranium, minus 4.002603 U, that is the rest mass of the alpha particle. That are all the calculated rest masses of all elements into 931.5 mega electron volt divided by U. If we calculate this equation, we will get the answer 5.87 mega electron volt. This is the amount of the energy that is released during this reaction. As you can see that this value is greater than 0, so we concluded that the Q value is greater than 0, so this reaction will be possible and it is possible for plutonium to do alpha decay. In previous slides, we have discussed about the conservation of energy. We have done a sample problem. We calculated the Q value. What is the importance of the Q value in the alpha decay? Now we will discuss about the conservation of momentum. How we can calculate the conservation of momentum in alpha decay? We will try to calculate the value of the Q in terms of the momentum. If the original nucleus X is at rest, then its linear momentum is 0. Obviously, we have considered our regional or parent nuclei X at rest as we discussed in previous slides. When velocity is 0, the momentum, that is the product of mass and velocity, it also becomes 0. So according to conservation of linear momentum, the momentum before on one side must be equal to the momentum on the other side. But in previous slides we discussed that our parent nuclei is at rest, but the daughter nuclei and alpha particle are moving with some kinetic energy. As we discussed, our parent nuclei is at rest and its momentum is zero. So momentum on one side is zero. But on the other side of the equation, our daughter nuclei and alpha particle is moving with some kinetic energy. In order to conserve the momentum on both sides, we will consider it that our daughter nuclei and alpha particles moves with equal and opposite momentum in order that final momentum also be zero, and our law of conservation of momentum holds here. So as we discussed that our daughter nuclei and alpha particle will have equal but opposite in direction, so their momentum can be written as P alpha is equal to P x bar. As we know that there is a relation between kinetic energy and momentum in physics that can be written as kinetic energy is equal to P square over 2m. Here in this topic we are representing kinetic energy by T, so we can write that T is equal to P square over 2m. As we discussed in conservation of energy, Q value can be written in terms of the kinetic energy as Q is equal to T alpha plus P alpha square 2ma. In this equation, P is the momentum, mx bar is the rest mass of the daughter nucleus, m alpha is the rest mass of the alpha particle. Q is equal to, next equation becomes Q is equal to P square alpha over 2m alpha into 1 plus m alpha over mx bar. This equation comes from if we replace our above equation by using equation 3 in which P alpha is equal to Px bar. Our equation using equation third, our equation become Q is equal to P square alpha over 2ma alpha into 1 plus m alpha over mx bar. As we know that P square alpha over 2m alpha is equal to the T alpha, that is the kinetic energy of alpha particle. So it becomes Q is equal to 2T alpha into 1 plus m alpha over mx bar. If we want to calculate T alpha, then we can write above equation as T alpha is equal to Q over 1 plus m alpha over mx bar. As we know that mass of the alpha particle is 4, putting the value of mass of alpha particle, that is 4 over the mass of the daughter nuclei will decrease by a minus 4, so it becomes a minus 4. Putting all these values, we will get new equation T alpha is equal to Q over 1 plus 4 over a minus 4. If we solve above equation, it becomes T alpha is equal to Q 1 minus 4 over a. This is the value, this is the equation for the kinetic energy of alpha particle. If we solve above equation for a greater than 4, it has been shown that about all the Q value or the released energy in the spontaneous emission of decay is carried by alpha particle. It has been shown that typically 98% of the energy released is carried by alpha particle and only 2% by nearly nucleus X bar. If alpha decay is a part of decay chain, then recoiling daughter nucleus may itself be radioactive, and these recoils can result in the spread of radioactive material. It must be noted here. As in previous slide, we have calculated the relation between kinetic energy and the Q value. The kinetic energy of an alpha particle can be easily directly measured with the magnetic spectrometer, that is a device used widely in the experiments of the physics. And when we calculate the value of the kinetic energy by just putting simply in the equation, we can easily calculate the value of the q of a decay. This gives us a way to determine atomic masses, such as in a case in which we might know the mass of long-lived X as a result of direct measurement. But X bar is so short-lived that its mass cannot be determined by direct measurement. In such cases, X bar, that is the data nuclei, it itself decays into an other element. So in order to measure the mass of the data nuclei, we use this method. This is the energy level diagram for alpha particle decay. In this energy level diagram, the vertical scale shows the nuclear mass or the equivalent energy. The parent nucleus, that is represented by X, is placed at a level on the mass equal to its own mass, and the data nucleus, that is Y, is placed at a level on the mass scale equal to its own mass along with the mass of alpha particle. As we know that when parent nuclei form data nuclei in alpha decay, there must be a alpha particle. This vertical between the level, that is the mass of parent nuclei, and mass of the data nuclei with alpha particle, it shows the energy difference or the Q value. The energy level diagram for this is the energy level diagram for plutonium 242-94. This illustrates a situation in which alpha particles of different energies can be emitted. The corresponding Q values are 4.983, 4.835 and 4.676 mega electron volt. The value of the alpha's kinetic energy in each transition is less than Q. Due to the recoil energy of data nucleus, that is the uranium, transition to higher excited state of uranium not shown have transition probabilities too small to be significant. We can say that the available energy Q alpha goes into the kinetic energies of the alpha particle and of the recoil of data nucleus. This is all illustrated in the graph. If Q alpha is greater than 0, alpha decay is energetically possible. However, it may not occur for these other reasons. At the top of the graph, we have written the formula of the Q value that we discussed in the previous slide. That is equal to the mass of the parent nucleus minus mass of the data nucleus minus mass of the alpha particle into C square. This is the formula to calculate the Q value for the reaction. This slide shows the series of decay and Q value and mean value. In this slide, we will know about how Q value and mean life of any decay are related. This table shows the steps for the naturally occurring radioactive series with the module 4 is equal to 2, that is alpha particle. Our main interest in this graph are alpha decay, Q values and the mean lives. In this graph, when we will compare Q value and mean lives, we will see that there is a strong correlation between increasing Q values and decreasing mean life. It means that when the Q value is high, the mean life is short, but for very long lifetime the Q value becomes short. There is a series of the decay series. When uranium goes into the different transitions through alpha decay and beta decay, the Q values are mentioned and then mean lifetime is also mentioned. You can see that uranium first of all goes into the thallium through alpha decay, that goes into the Pa through beta minus decay, that again goes into the uranium through beta minus decay. Then the uranium again goes to thallium through alpha decay. Thallium goes to radium through alpha decay, that goes into the radon through alpha decay. This change goes up to the lead 82, starts from uranium. The Q values for all the decays are mentioned and the mean lifetimes are also mentioned. When we compare the mean lifetime and Q values, we will see that there is a strong relation. For example, if we take first one, the Q value is 4.7 and the mean life is 6.45 into 10 to the power 9 years. But for second one, it becomes Q value is 4.86, but mean life is 3.53 and 10 to the power 5 years. If we compare first value with second value, we can clearly notice that Q value increases from 4.27 to 4.86 values, but mean life decreases from 6.5 into 10 to the power 9 years to 3.53 into 10 to the power 5 years. So we can say that there is inverse relation between Q value and mean life. In this slide, we will discuss the behavior of the elements from atomic mass A is equal to 144 to A is equal to 206. From A is equal to 144 to atomic mass 206, there are basically 7 alpha emitters of naturally occurring nuclides. It means that there are 7 radioactive elements that undergoes the spontaneous emission of radiations through alpha decay. When we are finding the alpha emitter in this range of A that is mentioned above, the energies of the emitted radiations are normally less than 3 mega electron volt. As we discussed in previous slides, lower the energy release, the greater is the lifetime. Means to say that if Q value is less, the lifetime of the nuclide is greater. So the low value of the Q shows that their existence implies such great lifetime that is comparable or greater than the age of the earth. You can say about 4 into 10 to the power 9 years. That is the huge lifetime or great lifetime due to the low value of the Q or energy released. Most nuclei in this range on the line stability may be energetically able to decay by alpha emission. They do not do so at a detectable level because the transition rate is too small. In previous slides, we have discussed about the behavior of the elements for a atomic mass 144 to 206. In this slide, we will discuss how the elements for atomic mass greater than 206 with a proton number 82 behaves. Above Z is equal to 82, many naturally occurring alpha emitters are found, many with short lives. In previous slide, we discussed that the Q value for elements lies in the range of A is equal to 144 to 106. Their Q value is small, so their lifetime is very high. That may be compared with the age of Earth or may be greater than age of the Earth in some cases. But when we discuss this region where our mass is greater than 206 or atomic number is equal to or greater than 82, in these cases the energy released or Q value is extremely large. You can say that their lifetime is so short. Most of the heavy nuclei to be found on Earth were probably produced in one or more supernova explosions of early massive stars. When there are the explosions, most of the heavy nucleus were discovered or formed in the universe. Such explosions can produce very heavy nuclei, including transuranic elements. These transuranic elements are those elements whose atomic number is greater than 92 and their substitute decay by alpha emission. We'll take them down the periodic table in step of delta A that equal to -4. In these slides we have discussed about the behavior of the elements with atomic number greater than 206. In this slide we will discuss about the Geiger-Nuttall law. What is this law? Geiger and Nuttall are two scientists that noticed that alpha emitters with large disintegration energies had short half-lives and conversely. All these things we have discussed earlier in previous slides, that Q value and half lifetime is inversely proportional to each other. When the value of Q is large, the half-life is short and vice versa. For example, thallium-232, the half-life is 1.4 into 10 to the power 10 years and Q value is 4.08 mega electron volt. But if we discuss about the thallium-218, the half-life is 1.0 into 10 to the power -7 second. This is the so short half-life that it goes into the seconds. So Q value will be so large that can be Q is equal to 9.85 mega electron volt. The calculated formula is log T half is equal to A plus B over square root Q alpha. This is the Geiger-Nuttall law. The graph also shows the relation between half-life and alpha decay energy, that is Q in mega electron volt. The half-life is taken along y-axis and Q value is taken along x-axis. This graph also shows that for high value of Q, the lifetime becomes short and vice versa. Now we will discuss about the applications and importance of the alpha decay. First application is smoke detectors. This is the type of the detectors in which alpha decay is used. Americium is one frequently used element as it is a major source of the alpha particle. Inside the smoke detector, alpha particles are released. That released alpha particle in turn ionizes the air inside the detector. Smoke in the detector absorbs these alpha radiations, so if smoke is present in the ionization is altered and the alarm is triggered. Alpha particle X-ray spectroscopy, abbreviated as APX, are also used in a process known as APX. In this spectroscopy, alpha decay is used. This process is used to determine the elemental composition of rocks and soil. NASA also used this method in its mission to Mars, including to find out the path to determine what elements exist in Mars rocks. In the medical field, a new cancer treatment known as targeted alpha therapy or TAT uses alpha decay to kill cancer cells. Lead-212 is injected and travels to the site of the tumor to find out the tumor, then giving off alpha radiation which kills all the cells in this area. Thank you so much, students. Hopefully you have understand clearly about alpha decay. Thank you so much.